So the idea behind binary is that computers ultimately only recognize zeros and ones. Ones being the presence of electricity or being the presence of a charge on something, on a media, and then a zero being the absence of that charge. So humans count like this. I'm going to pretend that I'm an odometer in a car and I'm going to start driving. So I drive a mile. I drive another mile. I drive another mile. It's getting boring. I drive faster. There we go. What happens when I hit 9 and drive one more mile? Our numbering system, base 10, so-called because it has 10 digits. What are the 10 digits? 0 through 9. It rolls over when we hit 9, right? So when I drive one more mile, that 9 is going to change into a 0. And then what happens?
Carry the 1.
Yeah, we carry the 1. Okay. And so on. I'm not going to count up, But, and when I got to 0999, and then I drove one more mile, that one would turn into a 0, but we would carry the 1. That one would turn into a 0, but we would carry the 1. That one would turn into a 0, but we would carry the 1. And then when we were at 1999, the same thing would happen. That would change to a 0. We'd add 1 to that one. Whoops. That would turn into 0. We'd add 1 to that one. Whoops, that one turns to 0, and we go to like that. So we all know how to count in base 10. Been doing it since kindergarten or first grade or something. This place right here, this last column, is 10 to the power of 0. Now you know what 2 to the power of means. 10 to the power of 2 means 10 times 10. 10 to the power of 3 means 10 times 10 times 10. 10 to the power of 0 is a weird concept, but any number to the power of 0 is 1. So this is the ones column. 10 to the power of 0. Then the next one over is 10 to the power of 1. So this column right here, if that's the ones column, that's the tens column. Then we have 10 to the power of 2 as the next column. What's 10 to the power of 2 equal to? 100. Yeah, 10 times 10 is 100. So guess what this one is? Based on the same pattern, this is 10 to the power of what? 3, which makes it equal to what? 1,000. So that's the thousands place. So we have 1,000, 100, 10, and 1. So if we have this number, 2, 3, 8, 7, what that is can be considered is 2 times 10 to the 3, because we have to make this as long as possible, plus 3 times 10 to the power of 2, plus what? Now I'm here. So 8 times what? 10 to the power of 1, plus, what's next? 7 times 10 to the 0. Or I could have said 2 times 1,000 plus 3 times 100. That was supposed to be a plus. Plus what's next? I made it to past the 2 and the 3, so what's next? 8 times 10 plus 7 times 1. And we add all those together, and by some miracle, we get 2,387. That's because we converted from base 10 to base 10. It's like converting English to English, and it's not a real accomplishment. But we're not used to thinking of it in these terms of powers. We are. It's burned into our brains, but it's burned so well into our brains that we don't even think about it. So binary kind of behaves the same way. If we have 4 binary places, like this, and they start counting, binary means base 2. It's only got 2 digits. So instead of 0 through 9, it only goes up from 0 to 1. Okay, so I hop in my binary car. I drive a mile. Now I drive another mile. Whoops, there are no 2's for binary. So what's going to happen?
It's going to carry the 1, so you have 0.
Yeah, it resets back to 0 and carries the 1. So I drive a mile. Now, well, I can't go raise anything to a 2, so that one resets to a 0, carry the 1. Whoops, there's already a 1 there. That one resets to a 0, carry the 1. Okay, there we go, like that. And I'm going to keep going. 1, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. What is the next number going to be? 1 followed by what? All zeros. Yeah. And then I could keep going. I'm going to cheat. I'm just going to grab these 8, paste them again, but change the first digit to 1. So in computerese, a binary number is called a bit. These are 4-bit numbers. An 8-bit number looks like this: 0, 0, 0, 0, 5, 6, 7, 8, like that, all the way up to 1, 1, 1, 1, 1. A 16-bit number has twice as many zeros as that. So your 8-bit Nintendo, you know, the maximum value its registers could hold, its processor could process, would be 8 bits, which had some consequences for the size of the graphics and the size of the programs that it could display and how many colors it could put on the screen. So it was pretty limited. Then the Super Nintendo and the Genesis came out, and it could hold a lot larger numbers, 16 bits. Then you bought your PlayStation, and it had 64 bits, and I'm not going to write 64 zeros. So I'm just going to stick with these 4 and these 8 bits and these 16 bits. So what is the value of this number here, 1111? Pardon me?
I went to immediately to hexadecimal.
Yeah, that's an F, but we'll get there. Okay, so just like we said, this is 10 to the power of 1, or 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3. We're going to say that this is 1 to the power of 0, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. So 2 to the power of 3, 2 to the power of 2, 2 to the power of 1, and 2 to the power of 0. Now, earlier I said anything to the power of 0 is what?
1.
Yeah, so that's a 1. What about 2 to the power of 1? That's just 2. And 2 squared is? You get the pattern real fast. So if we had 8 bits, that'd be the 1's place, 2's place, 4's place, 8 place, 16, 32, 64, and 128. So if we have this right here, 1111, that means 1 times 8 plus 1 times 4 plus 1 times 2 plus 1 times 1. And if we add all those together, we get 15. The largest value that could be conveyed with 4 bits is 15 if it's an unsigned number, meaning that we don't care about negative numbers. All we're doing is counting from 0 to 15. We could put the decimal equivalents, the base 10 equivalents, out here. That's a 0. That's a 1. Well, if this is the, I'm going to put the numbers 8421 out here in front of it. What is this one equal to? It doesn't have any 8s, it doesn't have any 4s, but it does have a 2, right? And it doesn't have any 1s, so when we add all those up, what is that? Okay, now you're just going to be able to pick out what's going on because of, you know, what's the next one obviously going to be? 3, 4. Let's pick a more interesting one. Let's skip a few, like that one. What is that one equal to? Does it have any 8s?
Yeah.
Does it have any 4s? Nope. Does it have a 2? Does it have any 1s? Nope. So that's equal to 8 plus 4, which is, 8 plus 2, so that's a 10. And you'd say it was an A. You are correct. We haven't talked about hexadecimal yet. We're getting there. So that's a 5, that's a 6, that's a 7, that's an 8, 9, 10, 11, 12, 13, 14, 15. And you can see why I stopped at 4-bit numbers. I don't feel like writing 8 ones on the screen and counting from 0 all the way up there. But what would 8 ones equal? Well, there's a mathematical formula that'll tell us the maximum value of 4 bits. And what it is 2 to the power of the number of bits minus 1. So if you have 4 bits, that's 2 to the power of 4 minus 1. Now right off the bat, I don't know what 2 to the power of 4 is, but I can figure it out. 2 times another 2 is 4, times another 2 is 8, times another 2 is 16. So, and then subtract 1 from it, the highest value that can be stored in 4 bits is 15. What about 8 bits? 2 to the power of 8 minus 1. Okay, now I'm extraordinarily lazy. I'm going to come up here and just type that into Google. 2 to the power of 8 minus 1. 255. So with 8 bits, you can count from 0 to 255, which is 256 different values. What about 16 bits? I could go type this in, but I actually happen to have it memorized. But go ahead and go to Google and type in 2 to the power of 16 minus 1 and tell me what it is.
Would be 65,535.
Right, 65535. Everybody knew what to type though, right? You could see what I typed on the screen. Maybe you couldn't. That's 2 arrow 8 minus 1. Or if you wanted to get 16, 2 to the power of 16. 2 arrow 16 minus 1. And what I'm calling arrow is shift 6. So the PlayStation 1 was a 64-bit device. 2 shift 6, 64 minus 1. That's a big number. That's 18 followed by 18 zeros. So that is why the PlayStation was so astronomically better than the 16-bit devices like the Genesis and the Super Nintendo in terms of the number of colors that they could display and the amount of memory that the device could access, because they were 64-bit devices rather than 16. Our computers are really large bit devices nowadays. You know, we're not limited to storing numbers only up to 256 or whatever. Okay, so let's go back to our worksheet. So the powers of 2 are 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. 1, 2, 4, and 8. And if you had to go further, you could. The powers of 10, 10 to the 0, 1, 2, and 3, which are 1, 10, 100, and 1,000. The cool thing about powers of 10 is that that number there just tells you how many zeros are in it until you wind up with negative powers. But 3 just means 1 followed by 3 zeros. Counting in binary we talked about. Now converting from binary to decimal. Here's our number, 1010. Well, I already did that one. But that's, I don't know why I put this many lines here, but there's a 1 in that column, so that's an 8. There's a 0 in this column, so that's not anything. There's a 1 in that column, so what does that one equal to? That's a 2. And then there's a 0 in this one, so that's a 0. I'm going to skip this line. I'm not sure what I had it there for. So the answer is 10 in base 10. Whenever I put a parentheses followed by a number after it, that means base 10. Just like a parentheses followed by a 2 is base 2. And if you want to get really funky, you can go and modify the size of the fonts to make the little subscript teeny tiny or whatever. But, you know, there we go. Do the next one yourself. 1001. Oh, great. I left the answer. Erase that line and do it again. Okay, so anyways, that's an 8, right? What is this one? This column. That's a 0, that's a 0, and what's that column? That's a 1. So 8 plus 1 is 9. Oh, and I left the answer here too. Dadgummit. Why did I give you all a completed worksheet? Okay, anyways. So with all 1s lit up, that means that it's an 8 plus a 4 plus a 2 plus a 1, which equals 15. Whoa, isn't that large? Really did not mean for it to be El Giganto like that. Whatever. I'm not going to take a lot of time trying to format this nicely. Okay, if I deleted a line up there, at least it put it on the same page, but who cares? So, in the 60s, if you were a programmer, you probably worked in something called Octal, which is a numbering system where instead of 10 digits, you only had 8 digits, the values 0 through 7. And the reason people did that is it was easy enough to convert in your brain from bits to octal numbers. You didn't have to add them up so cleanly. I mean, the way we did. However, we're going to skip octal because nobody uses it anymore, and we're going to use hexadecimal. Hexadecimal is base 16. We have 16 digits. Okay, that's pretty cool. Maybe if humans had been born with 8 fingers on each hand, we would use base 16 as well. How do you get 16 digits? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I want to go up to 16. What am I going to do next? I start using letters, where A is equal to 10, B is equal to 11, C is 12, D is 13, and so on, to where F is 15. So if you're counting until you roll over and carry a 1 over, the digits are 0 through 9, followed by A, B, C, D, E, and F. And that's just as opposed to making up, 6 new digits, triangle and smiley face and something like that, So if we make a little chart here, if you see an A, you know that that represents 10 in decimal. And if you see a B, that represents an 11. And a C is a 12, and so on. As long as you remember A is equal to 10, you've pretty much got it, because a B is 1 past A, right? And a C is 2 past A, so you can add 1 or 2 to 10 to get to it. If you're writing a number in hexadecimal, the powers aren't 1, 10, 100, and 1,000. They're 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, and 16 to the power of 3. So you get 1, 16, 256, and 496. So I'm going to scroll past this. This is showing how to count instead of counting in decimal. It's counting in hexadecimal. So 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Once you get to F, you roll over. 1, 0. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, all the way out to 1F. Then it rolls over to 2, 0, 2, 1, 2, 2. So I stopped here in that one. The example goes on afterwards. But what is 22 hexadecimal equal to in decimal? Well, we have a 2 in the 1 spot. Fortunately, that's real easy, right? 2 times 1 is 2. And then we have a 2 in this spot, which is no longer 10s, it's 16. So we have 2 times 16 plus 2. So 22, what's 2 times 16? 32, plus 2 more is 34. If we had the number, really? Okay, did not mean to do that. Takes it a minute to power up after you've turned it off. If you had the number 3,100 and A, no, 310A in hexadecimal, and you wanted to convert that into decimal, you have to remember those powers. That's 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, 16 to the power of 3. So we have, that is really sloppy. Let's try this harder. Try this again. 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, 16 to the power of 3. So that's a 1, that's a 16, that's a 256, and this is a 4,096, just because I remembered it from the page over there. So if we have this number, 310A, and that's base 16, and we want to convert that to base 10, we've got to do the same thing we were doing before, but the math is a lot nastier. That's the number we're trying to convert. What column is this A in? It's in the ones column, and what did we say an A was equal to? A 10. So that's equal to 10 times 1. This time I'm starting this way rather than that way, but we could have done it either way. This 0 is in the 16s column, but it's just 0. I'm just going to cross that out. This 1 is in the 256 column. So that's 1 times 256. Plus, lastly, we have 3 in the 4,096 column. I absolutely cannot do that in my head. Anybody have a calculator or type this into Google? What is 3 times 4,096? Okay, I'm going to need you to tell me again. I didn't quite hear.
12,288.
So that's equal to 12,288 plus 256 from that one plus 10. I might actually be able to do that. 8 plus 6 is 4, carry the 1. 9 plus 1 is 10, carry the 5. Okay. It's possible I got it right. If I did, then 310A is equal to 12,554. You get the idea. And if you had more hexadecimal digits, then you would keep going. 16 to the power of 4, 16 to the power of 5, 16 to the power of 6, and so on. Why? Why would anybody want to do that? That's horrible. But the reason why is we noticed earlier that the maximum value of 4 bits was what? 15. I can't find that now. Maybe it was on this sheet. Okay. What's the maximum value of a single digit in hexadecimal? 15. So we could do this. 0, 1, 2, 3, 4, 5, 6, 7, 8. It's going to be the same until we get to hex, the 10. That's an A. That's a B. That's a C. That's a D. That's an E. And that's an F. So if I had this series of bits, 0, 1, 1, 0, and I'm going to break them up by clusters of 4 after I do this. 1, 1, 0, 1, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 1, 1. Okay. I don't know how many that is. I'm going to break them up now by spaces. I'm not going to ask you to memorize that a D is a 101101 and that a B is a 1011. You could figure it out though. How could you figure it out? You just add up the 8, the 4s, and the 2s and the 1s, and you get like a 13 or whatever. and you think, okay, 13 is this how many past A? Okay, A, B, C, D. You count on your fingers and you get that it's a D. Whenever I ask you to do this kind of stuff, I will give you a table like this. So that's the binary. This is the decimal. And this is the hexadecimal. So now we have these numbers down here, these bits. If you wanted to display on the screen these bits, here's what you could do. You could convert them to decimal. Let's do that. What is an 0110? Tell me, looking it up. That's a 6. And what's next? Let's do decimal. So that's a 13. Okay, already I have a problem. I don't know whether these things are supposed to take up one digit or two. What's a 0001? That's just a 1. What is a...
8 and 30.
So that's an 8, right? 8 followed by a 3. Okay, so we had a problem. This one actually took up 2 spaces rather than 1. So in order to be absolutely sure that that is a 6, 13, 183, I would really need to preface them with zeros to indicate what they were if I wasn't going to space them out. Like that. That is an accurate transcription of those bits. I seem to have done something wrong.
You put a 0 in front of a 13.
And then you put a 0.
Yeah, thanks. Okay, there we go. That look better?
Yes.
Okay, so that's great. If I wanted to display some bits on the screen in numeric form in such a way that, you know, because what would happen if you had just a whole screen full of zeros and ones? Would you like looking at that? No, not really. You know, if you like the matrix and you have those numbers falling down and stuff like that, yeah, great. It's nice to have zeros and ones. But otherwise, you want something that's a little bit more interpretable. However, there's a more efficient way of displaying it than using 2 digits per 4-bit cluster. I'm going to take all these out, all these spaces out. And that's to use hex. So what is 0110 in hex? It's still a 6. What's the next one? D. What's the next one? 1, 8, 3. Okay. It took up half the space to display it in hex. Now the reason people used octal is that you could cluster them in 3 bits. 3 digits was enough to translate directly from binary to octal. So if you did this kind of stuff all day long for weeks on end, you'd know instantly that a D was a 1101 and that an 8 was a, you know, whatever. You don't really know, but you could see the utility, I hope, of having this as a hexadecimal display. Let me give you an example of when you might see something like that. There are tools known as hex editors. And a hex editor is something that will open a file and display its contents in terms of hexadecimal values. Go to your desktop, right-click, and create a text document. I already had one called boilerplate.txt, but just right-click, new text document, and type, well, whatever it's called. Then open it and type hello world or something like that. And then hit enter. And then type goodbye. Save that. Doesn't matter what you call it as long as you remember its name. Then open up your favorite browser and go to the site hexed.it. No, you can't really see it, so I'm going to go and type it in my text document. Go to hexed.it, hexedit. Get this thing. Do open file and go and find that file that you just created on the desktop. Mine was called New Text Document. Very creative name. Click Open. What we see here is some text, and I know you can't see it on the screen, that's why I'm having you do it in front of you as well. You see some ASCII text. We haven't defined what the word ASCII is, but when you type letters in, they have to be saved somehow on the computer. And then we see the hexadecimal values that correspond to that. So a capital H is the same as a hexadecimal 48. And a capital W, we could figure out, is the same as a, I don't know, one of those. And as you move your cursor left and right, you could figure, out which one corresponds to which. If I click on the W, then an uppercase W in ASCII, in hexadecimal, is a 77. And so we're getting an idea of the structure of the data as it's saved on a hard drive or as it's saved in computer memory.
When it gives you the binary next to it too.
Pardon me?
It gives you the binary down to the left.
Oh, I hadn't noticed that. So if I click on the W, there's the 8-bit integer. Yeah, you got all sorts of choices, and here's the binary right here in these little filled circles. So this 77 in binary, well, what did we decide a 7 might be? It's a 0, 1, 1, 1. And so 77 is 0, 1, 1, 1, 0, 1, 1, 1. That's cool. I hadn't noticed that. All right, so hexadecimal is a way of displaying binary numbers in a way where you could pack more information on the screen than if you were just displaying them as decimal numbers. That probably won't sell you on using it, in your everyday life. But if you're going into pretty much any branch of software development or cybersecurity or something like that, eventually you're going to wind up looking at a hexadecimal dump of data and trying to figure out what it is. For example, if I go and I'm going to find a JPEG. I want a picture. I want a picture of Snoopy. Okay. Who knows if this is really a JPEG, but we'll find out. I'm going to do a save as, save image as. I'm going to save that to the desktop. It's actually a PNG file and not a JPEG. The extension tells you in the computer what the data in the file is, what format it is, but also the bits tell the computer what the format is. So now I'm going to go back to Hexedit and I'm going to open that snoopy.jpg. I wonder if it's going to crash if I change the resolution to something a lot smaller, like 1020 by 768.